Hello and welcome to Chapter 4, Section 4. Today the first thing we're going to learn to do is how to construct perpendicular bisectors. Now please remember that the word perpendicular means that it intersects at exactly 90 degrees. And the shorthand for perpendicular is that. Now what we're going to do, we're going to start by constructing a straight line connecting with two endpoints A and B. What we want to do is draw a line that's perpendicular to this and that bisects it. So using our compass and making sure that our compass is open to more than half of our line, we're going to draw an arc from point A and an arc from point B. What I've done is I've drawn two parts of a circle with the exact same radius, which means that every point on this line is the same distance to B. And every point on this line is the same distance to A, and I used the same opening measurement, so they're all equal to each other. Which means at this point and at this point is the same distance from both A and B. This point is the same distance from both A and B. If I connect these two, not only are they perpendicular, but they are the same distance from point A and B. That makes this perpendicular, and it makes this a bisector. And this is how we indicate perpendicular and bisector. Now we're going to learn how to construct a line that's perpendicular to any random line through point P. Now point P is not necessarily in the center, but that's okay. We are going to open our compass wider than the distance from point P to the line, and we are going to draw an arc, oops, but I don't want it to be actually longer than the line itself, through the line like this. Now we know that this point is the same distance from point P as that point. When we draw, now I've got my point A and point B. Now I'm going to do this again. From point A, I'm going to draw an arc. And from point B, I'm going to draw an arc with the same radius as that from point A. Notice I didn't cross point P either time. That's okay, because when I connect that dot and that dot, it goes right through point P. So now, while I have a perpendicular bisector from point A to point B, I don't necessarily care about this. What I care about is that it goes through P and it is perpendicular. That's what I wanted, a perpendicular line, perpendicular to L through point P. The perpendicular bisector theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of a segment. And it asks us to prove this. Now let's think about this. We have a perpendicular bisector. If a point is on a perpendicular bisector of a segment, then it is equal distance from the endpoints of that segment, if that segment had endpoints. It's equally distant from both of these. And when we think about the radius that we were drawing with our compass making a circle, we know that every point on this line, we know that this line is exactly in the middle here. The question is this point up here exactly the same distance from both points? We can use a reflection to prove this. If I were to fold this piece of paper in half, and this is A and this is B, then because these are equidistant, you know that B would exactly fall on top of A. And P would be on this fold. And because P is a distance from A, and A and B are in the same spot, then P is also the same distance from B. So these two lines are the same. And you can do that using a reflection. Now, I'd like you to pause here and reflect question number 3 so that can kind of settle into your head for a minute. Come back when you're done. JK equals JL because J lies on the perpendicular bisector of KL. Make sense? Pause here and do your turn numbers 4 and 5. DC is the same as DA. They're both 20 centimeters because D is on the perpendicular bisector. So DC and DA are the same length. Number 5, BC is the same length as BA. Both of them are 25 centimeters for the same reason. The next thing we're going to do is prove the converse of the perpendicular bisector theorem. Now we're going to start by quickly going through the Pythagorean theorem again. In a right triangle, we know that a squared plus b squared equals c squared. When we draw a right triangle where there are 2 legs and a hypotenuse, and these two are a and b squared, and it doesn't matter which one is which, but the hypotenuse is always c. When you take this number and square it and this number and square it, it always equals this number squared, and then you just find the square root of all of those numbers to find out the actual lengths. We're going to use that to help us with the converse of the perpendicular bisector theorem. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector. So we switched them. We were talking about if it lies on the bisector, then it's equidistant. Now we're saying if it's equidistant, then it lies on the perpendicular bisector. So here we have triangle APB with a Q down at the bottom of P. We know that AP and PB are the same length. What we want to do is prove that P is on the perpendicular bisector of AB. Is line PQ the perpendicular bisector of line AB? So we're going to work through that proof. We have 2 triangles. We have APQ and BPQ. We know that AP and BP are the same. That's given. We know that PQ and PQ are the same. That's just an identity property. We know that these 2 are right triangles because that point is given also. If we lay these out so that PQ squared plus AQ squared equals AP squared, and PQ squared plus BQ squared equals PB squared, we know that AP squared and BP squared are equal. And we know that PQ and PQ are equal because they're the same thing. And because these 2 are equal, that must mean that this third one is equal as well. So here we're using math to prove our point. Pause here to do reflection number 6 and your turn number 7. Come back when you're done. For number 6, the square root of the 2 equal numbers are going to be equal. It doesn't matter how many times you find the square root. If it's the same number, that's going to be the equal thing. Now with number 7, we've got triangle ABCD here. We know that AD is 10 and that AD is 10 and BD is 6, and it wants us to find AC, this distance here. So we know that D is equidistant from A and C. These 2 are equal. We know that DB is perpendicular to AC because they've told us this. That means that DB is a perpendicular bisector of AC. That means if we can find this line, then we can double it to find this line. And we can use the Pythagorean theorem to solve this problem. If this is 6 and this is a right triangle and this is 10, this is 6 squared plus a squared equals 10 squared. So let's do that math. If AB squared plus BD squared is AD squared, 6 squared and 10 squared, we've got 100 minus 36, AB equals 60, AB squared equals 64, which means AB equals 8. BC also equals 8, therefore AC equals 16. Proving theorems about right angles. If two lines intersect to form one right angle, then they are perpendicular and they make 4 right angles. So here you're given a picture where two lines intersect and it tells you that measure of angle 1 is 90. And what it wants you to prove is that all of them are 90. Well, the picture shows that angles 1 and 2 are linear. And that means that 1 plus 2 equals 180 degrees because that's the linear pair theorem and the definition of supplementary angles. So we know that 90 degrees plus the measure of angle 2 is 180 degrees because we just substituted that. And because we can do subtraction, we know that 180 minus 90 is going to give us the measure of angle 2, which is also 90 degrees. So this gives us the measure of angle 2. We know that the measure of angle 2 equals the measure of angle 4. Now we could do that because they're vertical angles, or we could do that because 1 and 4 are linear angles as well. And we could do 1 and 3 are linear, are vertical angles, and that will give us 3. And, or, you know, you can do it any of those ways. But you do, when you claim something, you have to give a reason why you claim it. Okay? In example 3b, if two intersecting lines form a linear pair of angles with equal measures, then the lines are perpendicular. So we are given that the measure of angle 1 equals the measure of angle 2, and we want to prove that line L is perpendicular to line M. We know that angle 1 equals angle 2. We know that angle 1 plus angle 2 equals 180 because they are a linear pair. So that we know that because of substitution, and because they are the same, if we take that 180 degrees and divide it by 2, which is just the division property, then they both equal 90 degrees. Measure of angle 1 is 90, measure of angle 2 is 90. Therefore, line L is perpendicular to line M based on the definition of perpendicular lines. So go through reflect number 8, your turn number 9, and the elaborate questions numbers 10 and 11. Pause here and come back when you're done.
Elaborate question.
Number 8, if two intersecting lines are parallel, then they form a linear pair of angles with equal measures. Well, this is just the opposite of this. Yes, it's true. Number 9, the measure of angle 1 is the same as the measure of angle 3. They're both 50 degrees because of the corresponding angles theorem. And the measure of angle 3 plus the measure of angle 4, because it's a linear pair with angle 5. And angle 5 equals 90 degrees, that was given. So we know that angle 3 plus angle 4 is also equal to 90 degrees. If the measure of angle 3 is 50 degrees and the measure of angle 3 plus 4 equals 90, then 90 minus 50 equals 40 degrees, which is the measure of angle 4.